Have you ever really wondered what makes steel strong enough to build skyscrapers or to power these massive engines we rely on every day? We're literally surrounded by this incredible material, but its true power comes from a secret world, hidden deep down in its atomic structure. So stick with me, and let's uncover the atomic recipe that forges this incredible strength. I mean, just look at these gear teeth. Think about the incredible forces they have to withstand, meshing together thousands of times a minute without ever failing. And what are they made of? Well, it's basically just iron and a little tiny bit of carbon, some of the most common elements on Earth. So how on earth do they do it?
So what is it? What gives metal this incredible strength? The answer, you'll see, isn't just about melting it down and pouring it into a mold. No. It's a carefully controlled process of transformation, a journey of fire and force that all starts with a single, fundamental partnership at the atomic level.
And that partnership is an alloy. See, to really understand steel, we've got to start with the basics, with the fundamental science of what happens when we mix different elements together, atom by atom. So, what is an alloy? It's pretty simple, really. It's a material you get by mixing two or more elements, as long as one of them is a metal. You can think of it like baking a cake. The final thing you get is totally different from any of the individual ingredients you started with. And this is a really big deal. The vast majority of metals we use in engineering today are alloys. And why is that? Well, it's because pure metals, like pure iron, are actually often way too soft or have other big limitations. Alloying is how we unlock their true potential. Now, these atoms can mix in a couple of different ways. Over on the left, you've got substitutional mixing. That's where new atoms kind of kick out the old ones and take their place. But steel does something really special, which you see on the right. The tiny carbon atoms don't replace the big iron atoms. They actually squeeze into the gaps between them. This is called an interstitial alloy. And that right there, that's the very first secret to steel's hidden strength. Okay, so we've got our mix of iron and carbon. But how do we turn that simple mixture into something like high-performance steel? For that, we're going to need a map, a transformation map that tells us exactly what to do and when. And here it is, the iron-carbon phase diagram. Now, I know, it looks a little intimidating, but trust me, just think of it like a treasure map. Each region on this map is a different phase or state that steel can be in, and it all depends on its temperature and how much carbon is in the mix. We're just going to focus on the most important destinations for our journey to strength. All right, our first stop is ferrite. This is the normal, stable state of steel when it's just sitting at room temperature. It's pretty soft, it's ductile, meaning it can bend without breaking, and as you can see, it can only hold a tiny fraction of carbon in its structure. This is our starting point. Okay, now let's turn up the heat. When you get above about 727 degrees Celsius, the iron atoms literally rearrange themselves into a new structure called austenite. And this is the gateway to transformation. Its atomic structure has much bigger gaps, which lets it dissolve over 2% carbon. That's almost 100 times more than ferrite. This is the phase where we load the steel up with potential. And our final key destination on the map is cementite. Now, this isn't just a simple mix. It's a whole new chemical compound made of iron and carbon. And its most important feature? It's extremely hard, but also very brittle. This is the raw ingredient for strength in our recipe. So, we've seen the map and we've met the key players. You've got soft ferrite, super absorbent austenite, and hard as nails cementite. Now it's time for the main event. Let's see how we combine all of them through a trial by fire to create something truly extraordinary. So here's the 3-step recipe. First, we heat the steel up into that austenite phase to get all that carbon dissolved nice and evenly. Second, we cool it down really fast, a process called quenching. And third, we give it a gentle reheat, which is called tempering, to get the final product just right. And right here, this is the most critical step in action. If we cool that austenate down slowly, the carbon atoms have plenty of time to move around and form these neat, alternating layers of soft ferrite and hard cementite. But if we plunge it into cold water or oil, the carbon atoms get trapped. They literally don't have time to escape. This creates a brand new, distorted, and super strained structure called martensite, and that is the secret to hardness. The martensite that we just created is incredibly hard, but it has a fatal flaw, just like our source material says. It's also extremely brittle. It's kind of like glass. It's strong, but if you hit it, it'll shatter into a million pieces. So our steel is hard, but it's not actually useful yet. And that's where that final step, tempering comes in to save the day. By gently reheating the steel, we let some of those trapped carbon atoms move just a little bit. It's enough to relieve all that intense internal stress inside the martensite structure. And this is what transforms the brittle steel into something truly resilient that can actually absorb an impact. Just look at this trade-off. It's amazing. We start with pure martensite. You've got maximum hardness, but dangerously low toughness. But after tempering, yeah, we sacrifice maybe 15% of that peak hardness, but in return, look at the toughness. It skyrockets. We've just created a material that is both incredibly hard and incredibly tough. So we have the recipe, we know the process, but in the real world, you often don't want a part to be the exact same all the way through. So let's see how engineers apply these principles to create the perfect component. Let's go all the way back to our gear to see how this all comes together. The secret here is that the gear isn't one uniform thing. The surface and the core are engineered to have completely different properties. That surface goes through the whole intense hardening transformation, but the core is kept tough and resilient. And the goal here is just brilliant engineering. What you want is a super hard surface that won't wear down from all that friction, combined with a tougher, more flexible core that can absorb the shock of an impact without shattering the whole gear. It's the best of both worlds. And this is done through processes called case hardening. For example, in carburizing, you actually add extra carbon, but just to the surface. Or in induction hardening, use a high-frequency current to heat only the outer layer before you quench it. Both of these methods create that hard martensitic case on the outside while leaving the inside, the core, tough and ductile. So you see, the secret strength of steel isn't just one thing. It's a dynamic, controllable recipe of atomic structure, heat, and time. It's a process that lets us craft a material with the exact properties we need, right where we need them. From that first atomic partnership to a trial by fire, we forged a new understanding. Now you know the recipe for strength. So, what will you build?